You've heard of ChatGPT, right? Of course you have. But have you ever stopped to wonder what actually makes it tick? Well, it turns out a huge part of the answer goes back to a single research paper from 2017, a paper with a really bold title, Attention is All You Need. Now, this wasn't just another boring academic paper. No, this was a seismic shift that laid the foundation for pretty much all the modern AI we use today. So, let's dive in and see how this one paper totally rewrote the rules.
To really get why this paper was such a big deal, we have to start with a really fundamental question, the exact problem these researchers were trying to solve. How does an AI actually read a sentence, figure out what it means, and then maybe translate it into another language?
For a long time, the standard approach was, well, kind of painful and incredibly slow. Models had to process a sentence sequentially, just like this, one single word at a time. And as you can probably guess, this created a massive bottleneck. The dominant models back then were called recurrent neural networks, or RNNs for short. The way they worked was they'd read a word, update their internal memory of the sentence, and then move on to the next one. But this core process, what the paper calls their inherently sequential nature, was the whole problem. It meant they were slow, you couldn't really speed them up by throwing more computers at them, and they had a really hard time connecting words that were far apart in a long sentence.
Okay, so this slide just lays it all out, plain and simple. On the left, you've got the old way, the RNNs, slow and sequential. The further apart two words were, the longer the information had to travel, almost like a game of telephone. But the new idea, the transformer, it just throws that whole concept in the trash. It looks at all the words at the exact same time, in parallel. This makes it lightning fast. And, this is the key, the path between any two words is always just one step. Every word can talk directly to every other word.
And that brings us right to the money quote from the paper itself. They basically said, we're proposing a new, simple architecture called the transformer, and it's based only on this thing called attention. It completely got rid of that old, clunky step-by-step process. And yeah, this was the moment everything changed.
So what was this radical idea? It's actually beautifully simple when you get down to it. Instead of that one word at a time slog, what if a model could just look at the entire sentence at once and for every single word figure out which other words in that sentence were the most important for understanding it? That is the essence of self-attention.
And here it is. This is the diagram, the famous transformer architecture, right from the paper. Now, it might look a little complicated, but it's really just two main parts. On the left, you have the encoder, and its job is to read and understand the input sentence. Then on the right, you have the decoder, which takes that understanding and generates the output, like a translation.
So let's break it down a bit. Both the encoder and the decoder are actually stacks of 6 identical layers piled on top of each other. This lets the model build a progressively deeper and richer understanding. And notice what's missing? There are no recurrent bits anywhere. The engine that drives this whole thing is a component called multi-head attention.
Okay, wait a second. This brings up a pretty obvious problem, right? If the model sees all the words at the same time, how on earth does it know the difference between the dog chased the cat and the cat chased the dog? The meaning is totally different. How does it get that sense of sequence?
The solution is just genius. It's called positional encoding. Before the words even enter the network, the model adds a little unique mathematical signal to each one. Think of it like a GPS coordinate for each word. This signal, which is generated using some clever math with sine and cosine waves, explicitly tells the model, hey, this word is in position 1, this one's in position 2, and so on. Problem solved.
Now let's look at the real heart of the machine, attention. The diagram on the left shows the basic calculation, called scaled dot product attention. But the transformer is like, why do this once when you can do it multiple times? So it runs this calculation many times in parallel, which is what you see on the right. And that's what we call multi-head attention.
The best way to think about multi-head attention is to imagine a committee of 8 experts all reading the same sentence. One expert head might focus on grammar, another might track who is doing what to whom, and a third might be looking for connections between words that are really far apart. By running all 8 of these in parallel and then combining their insights, the model gets a much richer, more multifaceted understanding of the sentence.
As the authors put it, multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. Now that sounds a little academic, but what it really means is that it's not just about paying attention, it's about paying attention from multiple perspectives, all at the same time.
So this all sounds great in theory.
A faster, more parallel architecture that can see the whole sentence at once. But did it actually work? The proof is in the pudding, so let's look at the results.
Man, this table tells the whole story. On a standard translation test, the previous best models, even complex groups of models working together, could only hit a top score of 26.3. The transformer didn't just beat that, it absolutely smashed it, achieving a 28.4. And look at the training cost. It achieved this new record using nearly an order of magnitude less computation. That's insane.
To put that in perspective, improving the score by over 2.0 points, that's not just a small step. In the world of machine translation research, that is a massive leap forward. For a single new architecture to do that was just unheard of.
And this is the part that truly shocked the research community. This new state-of-the-art model was trained in just 3.5 days on only 8 GPUs. That was a tiny fraction of the training time and cost for the models it just completely outperformed. The takeaway was crystal clear. The slow, sequential processing of RNNs was no longer necessary. This new paradigm, built entirely on self-attention, was not only way more powerful, but also dramatically more efficient and scalable.
The legacy of this paper is literally all around us. The transformer architecture became the direct blueprint for almost every large language model that followed, including the GPT family and BERT. It kicked off the entire generative AI revolution we're living through today by showing that a relatively simple, highly parallel architecture could be scaled up to achieve incredible things.
And so, this one paper proved that for the problems of 2017, attention was indeed all you needed. Which leaves us with a fascinating final question to think about. As the world of AI continues to evolve, what will we need next?